and welcome to the MIT SDM Systems Thinking webinar series. My name is Naomi Gutierrez, and I will be the host for this meeting. Today's speaker is Dr. Brian Moser, Academic Director of the System Design and Management Program. He will discuss performance for grand challenges with model and experiment-based engineering teamwork. If you have questions for the presenter, please enter them into the chat window on your YouTube screen. They will be addressed during the Q&A portion of this meeting. Take it away, Brian.
Great, thank you, Naomi, and thank you to everyone who's dialing in from across the internet and taking your lunchtime or other time to listen today. We have an hour, I think, total. I'll try to take about 45 minutes to share two topics with you. The first is to give you an update on recent changes here at MIT in our STM curriculum. I'm happy to share with you some of the things that we've been doing to try to improve this graduate program and especially its core courses. Secondly, I'd like to share with you some of the research that my group has been leading that really ties to the first topic, which is exploring the nature of engineering teamwork to confront the new grand challenges of our time. So I will go pretty quickly, as is MIT fashion, through the content, and so feel free to ask questions through the chat, and Naomi will field those. And of course, this is being taped, and if you'd like to follow up afterwards, I'm happy to chat with you. If you haven't had an update or are not aware of SDM, SDM is the System Design and Management Program here at MIT. We are both in the School of Engineering and the Sloan School of Management. And from the very beginning of this program, we've been in partnership with industry. In fact, a group of 7 companies in the 1990s asked MIT to respond to strengthen their capability upstream, particularly in design and engineering of complex systems. In that tradition, we were the very first program here at MIT to grant a degree that was career compatible, including a distance option. The mission is quite clear. We would like to prepare leaders to solve the most complex systems problems that we're confronted with. And I think Tom Magnati, who was one of the first co-founders of STM, said it clearly. We're looking to educate those who want to lead rather than leave engineering. We're very lucky to have a terrific team here at STM. Our faculty co-directors are Steve Eppinger and Warren Searing. Steve, of course, from the School of Management, and Warren from the School of Engineering. Joan Rubin is the executive director, and we're joined by Amanda Peters in career development and Ben Linville-Engler in industry and certificate programs. Now, if you've worked with MIT, you realize that MIT is notable in that it works as a bottom-up institution. The barriers and boundaries are porous across this special place. And because of that, our students and our staff collaborate and work across the institute. That is our real strength. So in our core classes, which I'll tell you more about in the next 20 minutes or so, we are lucky to have Professor Ed Crowley, Dr. Bruce Cameron, Dr. Rebentish, Dr. Donna Rhodes, and myself leading those lectures, which, as you'll see, is quite a bit. It's 68 lectures over 9 months. And then there are a number of faculty who teach electives and depth classes, and many who, related to systems approaches, both in management and engineering, who advise our students. So, this is a great place to be with respect to both theory and practice for systems. Now, to confirm that, let me point out our current student demographics a little bit. The average age of our students here is 32 years old. So they have 8 to 10 years of experience. Some of these students are here for a full master's, graduate degree. Some of the students are here in a certificate program. If you're interested in that difference, I'm going to ask you to go online or send a note to find out more. But importantly, these students, both certificate and masters, come from a broad range of domains, both commercial and government, and various kinds of systems from energy to health to infrastructure, automotive, aerospace, and more. This is a very, very important mix. The fact that they have experience in the field, so they're professional students, but also that they stretch across various fields. Now, we've been around a while, and in 2012 or so, the question was asked, have we taken a look at our education? And before 2013, this was the basic model for our curriculum. There were several core classes, one in system architecture, another class in system engineering, a third class in project management, and there were foundation classes taken in engineering and management. Well, when we actually looked a little deeper and tried to uncover the topics being chosen, we asked, is this both up to date, and more importantly, is it coherent? So a committee of folks here from MIT, faculty, instructors, research scientists, as well as alum and industry representatives met over a period of sessions in 2012 and 2013 to untangle this mess that you see on the screen. And many of these topics are actually still absolutely relevant. The question is, what's the frame here? What's the coherence? And what does it imply for the path of our students through this curriculum? So let me share with you what we've done. Well, we thought significantly about the future that our students, not perhaps the very first job that they graduate into, but maybe their third job, the future that they will be responsible for and be leaders in. And we thought about the grand challenges of engineering. You may know it from the NAE in 2008. And we can think about the set of skills and capabilities and, most importantly, ways of thinking necessary to make a difference in these grand challenges. We can also see, this is from the World Economic Forum, the recent Future of Jobs report, that there's a set of skills that are recognized for people who will take leadership positions and make a difference for complex problem solving. So we kept these in mind, and we went back to those three core classes, system architecture, system engineering, and project management, and we began to reframe, think about how we wanted to deal with those programs. Of course, system architecture is about creating the concept for the system. This is an image from one of our colleagues of the Oceanarium in Lisbon, showing the concept and how the concept later became a driving, crystallizing force for the architecture of the facility itself. System engineering, of course, is about bringing that concept into a physical reality and doing so in a way that is safe, functional, and verifiable. And of course, project management is about then working with real-world stakeholders and resources and budgets and time to bring that, to implement that system. So we recognize that these three kinds of topics and these sets of decisions and the skills are coupled, particularly in complex systems. So we should not be teaching them separately, but we need to think about how to understand these together. We want our graduates to be involved in conceiving, engineering, and implementing impactful systems to solve these grand challenges. So what we've done is we've created one integrated common core where topics of SA, SE, and PM are taught from a systems thinking point of view and together, and it's incredibly rigorous. And this rigor is asking a lot of our students and mid-career students, but the evidence is now showing in terms of outcomes and other evaluations that we've made the right decision. Now, of course, what drives this thinking is when we look more specifically at the learning objectives within these three related topics, we need to define them better. We need to understand what we meant by them and how they're related to one another. So we define 30 learning objectives, 10 in system architecture, 10 in system engineering, and 10 in project management. Obviously, these are just the titles. There's definitions at the back of this deck, I think, which will share. But the key thing about these learning objectives, as we debated really what they meant from a principles point of view, not a tools or not even a methods point of view, but a set of principles and ways of thinking, we also had to debate how they related to one another. Based on that, we developed a curriculum that is 68 lectures, 68 recitations, 21 assignments, and a 5-month team project. It is 15 to 20 hours a week per student over the 9 months. Starting in the fall, we conduct several spirals. So we begin with a short spiral, just introducing the 3 topics in turn. Then in the fall, we focus on fundamentals about establishing architectures. What are the underlying principles and ways of representing architecture? What is a system? Who are stakeholders? And so forth. And in project management as well, we cover the classics. We look at the fundamentals of project management. In January, we begin to broaden the view by introducing complexity and uncertainty. And we have a set of intense activities here on campus for both the certificate and master students together that not only addresses uncertainty and complexity and how to deal with it, but also launches their spring project. And I'll tell you more about that spring project, team project, in a moment. And finally, in the spring, we begin to focus on control and synthesis of these complex systems. Of course, not only the technical system that's being developed, it could be a system, it could be a service or a product, but also the organization, the firms, and the stakeholder relationships necessary for that system to perform well. And that finally leads us to this integrative team project, which lasts 5 months, which requires them to use all the skills that we've been touching on over that period of time. Along the way, we've got guest speakers and case studies across various domains, including aerospace, health, energy, automotive, infrastructure, software, and others. So I hope that gives you an idea about how we've focused and untangled these topics, zeroed in on a set of learning objectives that are principles-based, and then developed a curriculum to match it. That team project is especially important. And this team project is a response by teams of students, typically a team of 4, to a sponsored project challenge, not a solution, but a problem that has been well framed by a government or industry sponsor, a real-world challenge. The challenge may still be fuzzy. In fact, that may be the most important aspect of it. But the students then spend the 5 months with some mentoring, both on campus and from the sponsors, to reframe the problem, to architect a solution, to consider the engineering of the solution, and to build an implementation plan, design an implementation plan related. You can see some of the teams, sponsors from the last few years. As an example, this last year we had 50 proposals from various sponsors, and in the end the students selected and self-organized around 22 of the 50 topics. Just briefly, without going into it, you can see that there's a broad diversity of both sponsors and kinds of programs. And I'd say the hallmark is that any response to these challenges is going to be technical across multiple engineering domains, often hardware, software, materials, controls, structures. So there's definitely a cross-functional engineering view that's required. And it's also true that the real-world deployment of these systems requires an understanding of both organization and stakeholder relationships. Now, this has been the setup. This has been what we did. We spent 3 years now deploying this fairly complicated course to, on average, 90 to 100 students each cohort. And we've got quite a large team here that helps to teach and to evaluate the courses. I guess in MIT fashion, we are very structured and rigorous about how we evaluate ourselves, including feedback from the students, feedback from their outcomes. And here's the key idea. All of the mechanisms we use to teach, the lectures, the recitations, the assignments. We understand how they relate to these learning objectives. So as we see that we've made a change in emphasis, new content, guest lecturers, we try to understand whether or not there is an impact on overall performance. So we spend each summer, we very rigorously go through both quantitative and qualitative feedback on how we're doing. So what we have in the end is a new curriculum that has this integrated core at its base. And there are still course requirements in engineering and management beyond that core, and as well as electives. And the set of foundation courses is a relatively small set of classes that students can choose to take. And these courses and foundations are very particularly systems related. And then there's a broad set of electives, pretty much anything in the catalog, close to almost anything in the catalog. Don't tell others I've said that, but we really want to encourage students to get out across MIT, cut across boundaries, and although we've got a long list of electives we might recommend, if a student has an argument for an elective, we'll let them go with it. And finally, a thesis for the master's students. The certificate students are a little bit different in that they take the core but no other courses, and then they have a capstone, which is often done with others from their company on a company-related topic. Okay. Well, we're almost wrapped up with this first part of today's discussion. One thing we recognize is that there are emerging a number of complex systems, what we call threads, that there are groups or cohorts within our cohort who come from certain backgrounds who are interested in certain grand challenges. And so we can see that beyond the core course, there's often work in biological systems, electromechanical products, new aerospace, infrastructure systems, smart cities, manufacturing, production, supply chain, certainly software, although software cuts across everything these days, as well as decision analytics, which does as well. So as we are guiding our students through this very diverse and bottom-up place at MIT, our understanding, our lens into these engineering classes we call depth has been quite helpful. All right, so that's, and I'm sure there are some questions, but maybe we'll come back at the end to the questions. But let me now switch gears a little bit and tell you about research that I've been especially interested in which has only been recently been feasible. Let me explain. My background originally is as a computer scientist, but working in product development. So I've been building tools for engineers in industry for 25 years before I came back to MIT. I'm very interested in how groups of people, how teams solve problems when confronted with complexity. And to do so, 15, 20 years ago, we would model it. We would do a lot of work building a model of how the teams interact, and we would simulate those models. I do a lot of agent-based modeling and so forth. Now, all the principles were based on existing research, ethnography, survey-based techniques. It was quite difficult 20 years ago, as you know, to really understand what's happening during engineering teamwork. That's completely changed, completely changed. And so now, although my work traditionally has been mostly around a model-based approach to understanding both systems and the teamwork around systems, we are now balancing that work to be significantly more empirical. That is, to both design experiments and to build digital twins that are tied directly to sensors in the field so that we can understand engineering teamwork in real time. So that's what I'm going to talk a little bit about in the next 20 minutes. The group that I lead is called the Global Teamwork Lab. I'm also on the faculty at the University of Tokyo. And we have a group of researchers and students at Tokyo and also here at MIT. Our focus is on what we call the teams of teams working on systems of systems. So in the same way that when we're doing systems modeling, we are thinking about a federated approach rather than a centralized systems approach. and understand that the domain knowledge and vocabulary that's used to represent and analyze separate systems might be different and have different foundations. It's also true with respect to the diverse set of teams and their functions and roles that have to come together to solve these complex problems. So that is the phenomenon. In our case, we're interested in looking at this phenomenon of engineering teamwork at the mesoscale. By mesoscale, I mean not so much looking at individuals in small teams, which there's been some good work and interesting work around many places, including the design thinking community, that looks at how both personalities and contribution and innovation affect how small teams become productive. We're also not interested in the firm level, but we're interested in that size of the team of teams that tends to be the most dominant for making contributions in the kinds of engineering projects that we care about. So this is our focus, not at 7 people and not at 70,000 people, but at somewhere typically in a few hundred, which is where the rubber meets the road often to design and implement complex systems. So how are we going to do that? How are we going to study the phenomenon at this scale, the team-of-team scale? Well, there's 3 ingredients we believe are necessary in this research strategy. One is the systems of systems models, which we've been doing for some time. But by themselves, they're interesting and they're somewhat predictive. But they haven't been, until now, very deployable beyond the sets of experts or nerds like us who would use them. And yet the set of actors and decision makers who are in the field working often need to make decisions faster and don't per se know the details of these models. The second key ingredient is interactive visualization, which is not simply visualizing the aspects of a complex system and the decisions or the consequences of decisions, but for that visualization to be interactive. So as teams are working with a model, considering decisions, exploring decisions, we actually have sensors. We've instrumented that engineering environment based on that visualization. And third is then is a new and emerging teamwork science, which I think you've seen probably at other places as well, including here with Sandy Pentland at the Media Lab, which now suggests that if we can see at some level of granularity the attentions, the actions, the behaviors of teams when confronted with a particular situation, both problem and solution, then we can draw conclusions about it. So these 3 things in concert we think are necessary for us to dig deeper. That is, to understand the nature of teamwork while solving complex problems across boundaries. And of course, these boundaries are both functional boundaries in a cross-functional engineering sense, as well as cultural boundaries. Let me give you 2 examples in the next 10, 15 minutes, and then we'll open it up for discussion. The first challenge is a project with a consortium from the commercial maritime industry. And the challenge, of course, is their response to emissions. You may know that the IMO, their International Maritime Organization, has recently issued new requirements to deal with emissions. And this is a strong, very embedded traditional industry that in the last set of decades has been predominantly characterized by cost and size and scale. And the way to understand this challenge is that the set of decisions needed to make, let's say just in this example, the transition from heavy fuels to natural gas as one approach, that each actor must make their decisions in concert with others. If I would like a ship to transport natural gas or to use, I need to have bunkering facilities, I need to have local regulation, I need to have the shipbuilder know how to build it. So all these, even for a particular trade route, these need to be made in concert. So we began by thinking about and defining the system. And this is a level 1 OPM model. This is just the top view of the model. But as we began to think about the various value-producing functions of the system, We realize that there are pieces that are market-facing in shipping itself, in the port management, in port infrastructure, in regulations, and in shipbuilding. Let me show you the interactive visualization on top of a systems model and simulator that we developed. This is for a very particular trade route. And there's a set of decisions which are shown loosely on the upper left. A set of decisions for the particular portfolio of ships in the type of fuel that they use, the kind of port facilities needed, and the mix. And as we make and change decisions in what is effectively a morphological matrix across these stakeholders, we can see the propagating consequences, the emergent performance on the right. So the upper right shows us a set of ilities, basic efficiencies and costs in cargo moved, but also the new emissions requirements as well. So the complex system problem is, it's n-dimensional in the morphological matrix in terms of the way different players of this game will begin to, in some sense, think about and address the potential solution. But it's also n-dimensional in the problem space, that is, in the kinds of problem that's trying to be solved. So through this simulation and interactive visualization, we can see how the participants are interacting, how they're playing not only with the problem and the solution, but also in the way these workshops were conducted with one another. Let me move on. So we take the traditional systems model, we build it into a platform that has design of experiment and sensors woven in. We are looking for how to detect awareness, attention. By the way, awareness, think of this as the mental model coming in to the experiment and how that mental model may evolve over time, how that translates into attention, how attention into decisions, actions, interactions with one another, including disruptions and proactive interactions, the outcomes as predicted by the systems model, where there are surprises, and where there's learning. So we think of all of these things that we might attach a sensor to in these experiments as a socio-technical event. This event may be tied very closely to a technology suggestion or discovery around technology, but it also could be something that is about the behavior of these teams. In that, we want to map that socio-technical event to issues in the social space, the solution space, and the problem space. If we can do this, we believe that we will now be able to detect how these teams are framing and reframing the problem, what parts of the problem space they're paying attention to and not, what parts of the solution space they're actually exploring and converging on or not, how that relates to the engagement across the set of teams, and what that leads to or doesn't lead to in terms of emergent performance. Now, for that particular experiment I just showed you, the maritime experiment, here's an example. This experiment was run with industry representatives, so people from shipbuilders, ship owners, shipping companies, port management agencies, and so on. This shows us on the right the problem space. But what do I mean by problem space? Problem space are the set of performance characteristics we care about, the needs that are to be solved, the ilities, some might say. So each of the bands of rows here in different color is a different group that ran this experiment independently. So red, green, blue, I'm going down the list, orange, you can see a very different pattern of how they paid attention to the problem space over time during the experiment. And this example, this is just one of the teams here we're zooming in, and we can see a particular way that they focused on cargo, fuel, initial costs, and emissions differently as a pattern than others. Now, I'm not going to get into yet how we now analyze and detect significance of these patterns, but I want to show you that we're able now in real time to detect this interaction with the problem space as this team is working. Now, at the same time, we can see, based on the solutions or aspect of a solution through the morphological matrix that they are considering. They're discussing, because we have an ethnographer in the room, we're listening to audio, we're trying to see what's happening as the team is discussing. We can also see how they pay attention to and commit or make decisions related to the solution space. And here we can see, for example, in this small experiment, we can see were they actually exploring but not making changes? Were they making changes in fuel and bunkering, just in fuel choices, just in bunkering? So this is at a meta level of the kinds of changes that they were considering and making as they explored a trade space. And here's the key. So in the end, we want to see how this team, this group of humans, themselves, given their mental models, explored the trade space. That is, explored the problem, generated possible solutions, and they do this in a path-dependent way. And of course, it is different and a subset of what would be theoretically or mathematically possible. And for those of us who've worked in the field with engineers working on real-world class problems, we understand that. There's only so many hours in the week, and there's so much time to make decisions, and we can be supported by analytic tools, but in the end, our group, the team of teams, is having dialogue and attention on certain critical aspects or subparts of the problem and solution spaces. So here, if I look here again at this is the, of course, if we look at these are the entities, right? So this is the problem space, and each dot is an architecture, so it's a potential solution. The light gray dots here correspond to a computational approach. So this is the way we computationally searched the trade space and enumerated many options and evaluated them on cost. We can see from this workshop with people in the room, given this broad trade space, where did they go? Where were they actually taking their time? And these are people with background in judgment, at least for a subpart of the problem. And so we can begin to compare not only the teams to one another, but how these teams perform compared to some theoretical view of what could be possible and why. And by the way, it's not just the particular position or the Pareto non-dominant characteristic of one of these solutions for certain dimensions, but it's also the topological significance. If I go from one solution aspect to another and I'm going through it in a coherent way, we can now begin to see if they're making, if their search through the trade space has meaning, and when is it in that search through the trade space of meaning that they are triggering surprises and learning in a way that leads to better systemic outcomes. Okay, that was the first example. One more example, and then we'll wrap up. The second example is from my work I've been doing for some time in project management, which is to take for engineering, for complex systems, to go from project management being predominantly a process and practices-oriented profession to one that is now based on models and design. So we say that we should not be planning a project, we should be designing a project. And if I'm, for any typical product development project, if I'm thinking about how to organize not just the work, but also the organization, I might use a model-based approach to enumerate hundreds, if not thousands, of potential project plans and see what their emergent performance would be, and use that as a basis to come back with a recommended baseline plan. Let me show you a little bit about how that works. This is an example from the CDCAR project shown in the upper right, and this is again a high-level view. This is a model in a software called Teamport that shows 3 characteristics of any engineering project. And although the model under the hood is more complicated, it's very important that the model-based approach being used by a cross-functional team be useful in dialogue time, in the cadence of decision-making of these human folks. And as such, this model of the project is something that different cross-functional teams can come together and have a dialogue about in real time. So this model shows 3 things. It shows the product system itself, which is relevant, right? It is I may be swapping out subcomponents, I may be trying to understand scope and progress and risk with respect to the system being developed. rather than to process. This, though, does include process, or a classic work breakdown structure tied to phases of the project, but also includes teams, and teams not only by their capacity and capability, but teams by their structure. So all of these, right, these products and how they're organized in subsystems, the phases and how they're organized, and the teams come together to form the architecture of the project as connected by dependencies and allocation. So this is the design problem. To put it in simpler words, I've got work that has to get done. I've got workers and resources available. How do I put them together? What does that mean as an architecture of the project? Can I model that? And when I change something, can I see the emergent result? So with this particular project model that you see here, this is an example from this is actually from one of our classes here, of 20 groups in separate rooms working in parallel that were given a baseline model. And the baseline model was, I think, about a $10 million labor cost, so a moderate-sized program and a several-year program. And then they were asked to compete in a 2-hour period to generate as many meaningful new project alternatives as possible, improved on cost and schedule in this case. And again, I think the thing about this is, traditionally, if we are developing a project plan for a project, how many real variants of the project plan do we explore? Not just in Monte Carlo terms, but variation based on meaning in the ways that we can organize the work and organize the workers. So let me show you the results. This is a group that had no background, no understanding of this particular approach. But in 2 hours, they developed 316 new scenarios, new alternatives to the project plan without cutting scope, and ran nearly 1,500 simulations or forecasts of those scenarios. We can see in this diagram duration across the top. So this is almost 2.5 years, and $10 million for the baseline here. That some of the alternatives became more expensive or longer. But the great bulk is towards the utopia point, which is less cost and less time without sacrificing scope or at risk of quality. But notice that there's different colors, because the colors correspond to different teams. Let's parse that a little more. This is the 20 different teams, and we can begin to drill in and see that these teams in this same project modeling exercise behaved and performed differently. This is now where we want to turn the model-based approach into an experimental approach. We want to see more carefully what's going on. I can, in particular, compare this one team in the upper right, which had relatively few generated alternatives and stuck pretty much around the original baseline, and another team which seemed to have had not only been more generative, but also seemed to have made some breakthroughs. And so just as a hint, I'll tell you, we do pay attention to what's happening in the room, what the social relationships are amongst the parties, the degree that they interact, contribute, whether there's an alpha person in the room who's dominating, and so on. But we also look at what is it in their approach that allows them to jump beyond local minima, or at least local Pareto. So if you're interested in this work, I'm happy to share more, but we find this very exciting because now we can ask these questions again in real time because we've instrumented the teamwork platform. And this is an example. This is that same experiment where this is showing an animation in time where all the teams are exploring, making changes, and having effect. And some teams are kind of slow and methodical, making small changes and improvements. Some of the teams are taking wild guesses. And what's important to remember, for one team, that vector, that shift from one alternative to the next is an entire dialogue. There's design intent, there's hypotheses or assumptions that they have, and then they may either validate those or have a surprise and it doesn't work. And even if it doesn't work, they may or may not learn from it. So we're really trying to now dive deeply into the nature of the dialogue in the cross-functional team during this exploration to understand what's going on. And of course, the vision is to be able to see it and detect it in the future. So as I wrap up this pretty quick introduction to what we're doing, and I hope you've seen both about our education and some aspects of our research, I'll give you some hints for the kinds of research questions that our researchers and students are asking for engineering teamwork. And again, it much comes back to as we're able to detect and see how not just our engineers, but purchasing, engineering, supplier, manufacturing, the different parties in the cross-functional team for product development are engaged, can we see how their engagement relates to or responds to the framing of the problem, the generation of ideas during ideation, and how innovative those ideas are or are not? Can we see, as they're generating solution and solution aspects and alternatives, what the breadth is, right? Are they covering the ground or not? Can we see, as they're doing this, are they coordinating across critical interfaces of the system? Can we see evidence of surprise? That is an entrenched assumption that's well held, that's overturned, or a new piece of information that is contrary to expectations. And if there is a surprise, do we see that they react to it or not? Do they change their behavior? Are they detecting and handling errors? Are they conducting validation and verification in systemically relevant spots? And also, are they, through this whole process, in the way they react to what's working and what's not working, is it helping them to build capability for mid to long-term learning that lasts beyond the project at hand? So that's some of the questions that are being asked given this approach or this strategy for this research. And in the end, we want to be able to detect in real time, given a model and experiment-based approach, the health of the engineering project as a socio-technical system. And we find it incredibly exciting. We think that it will help us to uncover a new physics of socio-technical systems and a deeper understanding of engineering teamwork, and provide a new set of capabilities and skills and tools for engineering leaders. So with that, I'll just leave this on the screen for a second or two. I think you've heard from me today that, particularly for engineering teamwork and for project management, that I think there's some core elements that are included and that we've here tried to think about how to integrate these or to fold these into both our education and our research. Projects are not to be planned but designed, early and ongoing. Projects should be model-based, tied to digital twins, which are linked to sensors in the field for what's really going on, that we're focused on the mesoscale. And now suddenly we have a whole new set of capabilities to drive decisions through this instrumented teamwork that maps back to the problem space and the social space and the solution space. Thank you very much, and I'm now ready for questions. And I guess you're going to read some questions here from the... No questions.
Again, feel free to drop your questions in the chat if you have any.
It was all clear as mud. Can always talk more.
If you have any other points you'd like to express on anything like that while we wait for questions, or is it a 30 seconds?
No, I just a personal note that my background is I came back to MIT now 5 years ago as a part-time lecturer. I'd been in the field for 25 years, and some of the things that we're able to do today and think about today are, I really believe, going to transform how we conduct, how we build teams, how we evolve teams, and how we relate it to solving complex problems. So it's an incredibly exciting time to be involved in this work.
So we do have a question. Generally, startups work in move fast and break things culture. Does the course prepare them for that sort of culture, or do you think that's the wrong approach to start with?
So it's a great question. I think a better way to frame the question is, when is it, given the situation, better to in fact move fast, right? Whether it's agile or a prototype-oriented development approach, there is, both in terms of the marketplace and the nature of the technology itself, under what conditions would we choose to have even in relatively small teams, to move fast, not model, learn fast, and not. So we actually, I think it's a misnomer that strategy only makes sense for smaller new teams. There are plenty of times especially for uncertain, large, complex problems, where we might use selectionism or parallel work and other techniques to drive innovation faster. In the same way that the notion that a small team in uncertain necessarily should be less structured, that's also, I think, a fallacy.
All right, next question. How does the model measure innovation in teams?
Aha, the model. So I think so that's a research question about, given models and experiments in a particular design of experiment, how might we, given the sensors, either the model or the sensors that we're using, can expose innovation to us. I can give you one or two examples from particular research experiments, because that definition is part of that particular design of experiment. One is from our colleague, Professor Hori, at the University of Tokyo in the Japan Center for Japan Social Innovation Center. And we do workshops together in ideation. And the question is, there's two questions, how do we know that a set of ideas that emerge at the end of an ideation workshop, whether it's design thinking or another technique, are any good? And if you're only doing hackathons or ideation, it may be premature to judge whether or not the idea was good, but we still have to do it, right? The second question, though, is if there was a meaningfully good idea, that is, it's not only did that idea make it into some final successful product or service, but somehow along the way, that idea triggered a reframing of the problem, triggered a whole set of downstream decisions that led to that successful product. So if we want to do that, we now have to begin looking at, when was the idea first posited? Who posited it? Was it something stimulated by analogy? Was it by looking at a competitive work, and so forth? Was it a bias-breaking exercise? There's many techniques for ideation that we can look at. What we're seeing in our instrumented workshops is an improved ability to look at that path, that trace of when something immediately emerged and how it came through. And what we're seeing as an example is clearly that teams that have someone who comes up with a positive, strong idea early on, and it prematurely leads them to dismiss maybe quiet voices or other alternatives, have tended to do worse than those who perhaps hit the big idea later, which opened up the space bigger for them, or because of the way they've empowered participation, they not only have one idea, they have multiple, and they end up mixing them together. So the model doesn't proclaim what is innovative, the model is, and the sensors are trying to detect. I hope that answered the question.
Another question, do you have any example using this approach in a healthcare setting? And their example is hospital quality improvement.
Oh my goodness. Well, there's a few industries in this world that, I came out of aerospace and automotive, and when we're trying to fix things in a factory, we either stop the factory or we go build a new one. As you know well, in healthcare, that's hard to do, that you can't stop the hospital. There are both upstream in terms of R&D, pharmaceutical discovery and research. There's work going on here that I think a lot of the work until recently has been more about I'll call it the efficiency and coherence of that. A lot of the lean work, if you've followed Steve Spear or others, applying lean principles to healthcare. Often they treat healthcare as a process and try to identify waste and look for learning. And that's a key ingredient. We have not, in our immediate group, yet applied our work to healthcare, although we'd be happy to do so. I think this next layer above process and learning is now to understand what is it about the particular culture in the hospital or in the health group that can explain to us why either they are sufficiently or insufficiently generating improvements, tripping across surprises and responding to them. So hopefully this will allow us to see that more deeply. But no, I have not been directly involved.
All right, and one last question, unless anyone drops, oh, there are two more, never mind. But one of them was asking for some examples of the kinds of team projects that students do in their last 5 months of the course.
Sure, I think I have a slide in here. I can probably go try to find it just a sec. Here's the list. I'll put it back on, but I'll talk through this. Traditionally, a lot of the companies that sponsor, we've had government sponsors, so the city of Somerville sponsored a program looking at how they deal with the mix of investment in roads and safety in roads and maintenance in roads. And so our students developed a system that integrated detection of poor roads and maintenance tied to also responding to citizens in their response. They developed a kind of coherent approach. In healthcare, since that came up a moment ago, we've had several projects, including one this semester, one with IBM and Mass General Hospital on how do we decide in a patient-centered healthcare data environment. The particular case was tied to type 2 diabetes and post-diagnosis protocols and plan for the patient. And the students explored the mix of ways of ownership and management of the different types of data by the physician, by clinicians, by the patients, and came up with an architecture for that. We had another project with MGH, which was around pathology and digital pathology and what is and is not possible in potential transition to digital pathology and the barriers to it. And especially what was interesting in that case was the recognition that in a research hospital, how we adopt new capabilities and technologies is not very well rationalized yet. Aerospace, we've had a lot of flying cars the last few years. Flying cars for Airbus, flying cars for Toyota. We've had a fair amount of infrastructure related, future of construction and construction sites and other infrastructure. There was a blockchain boom about 3 years ago, which thankfully has kind of died off. I think we were seeing blockchain applied to just about anything. So I hope that gives you an idea, but we really look for industries that have inherently complex systems and send me a note, whoever asked the question, and I'm happy to send you a list.
And one more question, pretty specific. They asked what the software is that was used during the first maritime simulation example.
That was software that we wrote here. So with Global Teamwork Lab, we have a partnership where Ira Winder, who's here at MIT in course 11, helps us, in his team, help us doing the interfaces. And we build the simulation in concert with a group that's really good at that at Tokyo. And the modeling itself, the definition of the model comes from the domain folks. So yeah, that's all homegrown stuff. Any other questions? Can I go back to my thank you slide? Am I allowed to do that?
Yeah.
There you go. All right.
All right. Thank you to everyone who attended this webinar. The presentation slides and recording will be available in about 1 week and a link will be sent to all registrants with that recording and the slides. The next MIT SDM webinar for systems thinking will be held in May with details to come. Again, thank you for joining us.
Thank you, Naomi.